Hi, I'm Baihan Lin from Columbia University. Today, I'm going to share with you our demo system, SupervisorBot, NLP-Annotated real-time recommendations of psychotherapy treatment strategies with deep reinforcement learning. First, motivation. Conversational alignment, or working alliance, is a psychological concept that describes several important cognitive and emotional components of the relationship between two agents in a conversation. There are many important applications that can utilize this type of measurements. For instance, in psychotherapy, it has been shown that the working alliance between the therapist and the client has been a very important predictor of the final clinical outcome. Or if you are going to a business meeting, it's very delicate and you don't know what type of button might cost you a very important customer. Or if you work in a customer service business, the customer satisfaction can be greatly influenced by how well your conversation aligns with the need. You could also be in a show business where during a TV interview, you want to make sure your conversation is engaging and effective. Or if you're like me, or into law-related TV series, you will see that those lawyers always communicate with different type of people to gain the resources they need. In the educational context, if you're a teacher, you want the student to align with your goal. Finally, assessing the quality of the conversation can also help us to identify bad actors who are attacking a conversational system, like a bot. In psychotherapy, usually we have a patient and we have a therapist. And natural language processing techniques can help us to generate automatic annotations from audio inputs. However, what we actually want is beyond that. We also want to have a treatment companion system that can take these automatic annotations, which are actually some scoring system for clinically relevant insight annotation, and give us some strategies recommendations. For instance, what you should do in this scenario. However, it is complicated because patient's therapeutic landscape can be a dynamic maze, and the maze can change over time. And even after identifying the therapeutic state, we still need to find the best strategy to go through this maze. Its strategies are entangled with the theory of minds of patients, which is similar to an opponent in the game of Go. So as a result, we need to have a complicated decision-making system where the reinforcement learning method would be the best fit. As a result, we want to create a system that can record and transcribe the dialogue session in real time, assess the quality of the conversation in a turn-level resolution based on the conversational alignment, and doesn't require any pre-training or pre-registration or participant. Comparing to the existing method, usually it requires tons of audio data to train, and it requires the users to pre-register. Those are very important if you want to distinguish who is speaking at which moment. And also, during the deployment phase, old voice print cannot transfer to new users, and no learning happen after deployment. And users, they cannot interact to correct the system. In our cases, we would want the system to be having no pre-training. A similar profile can be transferred to new users, and the system can continually learn by interacting with the users. Here comes the methodology. Shown here is our analytical framework. You see, the input to our system is the continuous audio stream. We do not know who is speaking at which moment, and we utilize the online speaker diarization method to cut them into segments. And then, combining with the automatic speech recognition, we can separate it into transcripts belong to different users. When we have those user transcripts at real time, we can compare them with the inventory items of interest, which helps us quantify the quality of the conversation. That gave us the quality of alignment in different scoring scales. For the speaker diarization part, our system learns from scratch. It doesn't require user registration or pre-training. It does so in the following fashion. We process the voice print in sliding window fashion, and the agent will treat it as the context, and it will decide which user it belongs to. The users will then give it a feedback only sporadically about whether or not the agent made the correct choice or not. And then the agent will update based on this feedback. We formulate this as an online learning problem with episodic reward. Basically, at each time, the context is revealed to the player chose the action, and the feedback is only revealed given a probability less than 1. Then the player updates its policy. But in our case, it's slightly different because the options that the player can choose can actually even extend after the conversation begins. So for instance, if you are in a multi-person teleconference and someone else joined the conversation, you do not need to retrain your system. You can just tell the system on the fly, and maybe the system will even find out by its own, so it can extend its arm. And we propose to use the background episodically rewarded linear UCB, or Berlin UCB. In short, it's a semi-supervised learning bandit algorithm that utilizes a self-supervision module, in this case a clustering mechanism, to generate pseudo-feedback when the feedback is not revealed. Now we move on to the analysis of conversational alignment. Shown here are some examples of the inventory items. In this case, we are using the working alliance inventory. You can see those are statements. And then, according to different statements, there are also a key table which gave us its polarity. So for instance, in the task scale, question 2 is a plus, meaning that it is positively correlated with the task. If it is minus, it will mean it is anti-correlated. We can use this as a weighting matrix when we are computing our score in the 3 different scales. Here is an algorithm. Basically, you can potentially have inventories that corresponds to different users. Maybe there is an inventory for the therapist and an inventory for the client, and they're different. For instance, or in a TV interview, the interviewer and interviewee, they have their different criteria or rubrics to evaluate their quality. And then we can basically use the shared sentence or document embedding to embed those transcripts at the turn level and the document or the working inventory items in the embedding space. Then compute their cosine similarity. This can be visualized here in this flowchart, where after the diarization, for each user, we have the transcript, and the transcript is feeding to the deep embedding. In this analysis, we use the sentence spurt as our embedding. And then, the conversational quality would be measured as the pairwise cosine similarity of the current transcript versus the inventory items. Say, we have 36 inventory items, it will be a vector of 36 dimensions. And then, we can weight them by our alignment scale, and to compute the individual force in different scales. So there are 3 main components in our system. First, the speech processing unit utilizes diarization techniques to separate continuous audio input into dyads of the patient and therapist segment, and then transcribe it into natural languages. Natural language processing unit then tries to annotate some clinically relevant scores or ratings. Having those scores and ratings, we can collate a historical data for the recommendation system to train on. And the recommendation system, after being trained, can receive real-time input of the linguistic features and output recommended topics as if we're recommending a movie or things like that. So how do we formulate this into a reinforcement learning framework? As we can see from this figure, that it is more complicated than traditional reinforcement learning setting, where the agent simply interact with the world, and by taking action, and the world will assign some reward and state for it to update. Since now our environment consists of a dialogue interaction between the therapist and patient, only the therapist receives recommended action, and he or she has the option to choose to either take the advice or not take it. And after that, based on the interaction between the therapist and patient, we have a joint feedback as the reward to feedback to the recommendation agent. And as a result, the state also changed in the... So how did it work empirically? In the speaker diarization case, we evaluated it in mini-Vox, which is a simulation environment built upon Vox Silip and tries to mimic the scenario where the feedbacks are only revealed partially. Shown here is the result, where the cumulative reward is reported. The reward at each time step is 1 minus the diarization error rates. So in here, the reward is higher, the better. We see that in most cases, our Berlin UCB is doing better than the linear UCB, either when it is using the MFCC as the feature embedding, or a convolutional neural net, in this case is a VGG network to begin with. More systematic analysis suggested a similar trend. For the working alliance analysis, we tested it on the Alex tree dataset. This dataset consists of many psychotherapy sessions, which are transcribed and annotated by clinicians. Here's an example. You see the patient and therapist conversation in full here. Here's an example of the scores in different scales when we apply our methodology in one session. If we look deeper into the distribution of those scores, we can see that the bond scale appears to be positively correlated with the task scale, while the task scale is slightly anti-correlated with the goal scale, and it is colored by different clinical conditions like anxiety, depression, schizophrenia, and suicidal. We quickly notice that our alliance score is very predictive of the suicidality in those psychotherapy sessions. We also notice that when we're using different inventory items for the patient versus the therapist, we can see that those scales can be quite different. Doctors tends to overestimate their bond alignment, but underestimate their goal alignment. If we look at it in higher temporal resolution, we will see that different clinical conditions can have distinct dynamics across the session, as shown here. If we perform a regression, we see see a similar trend. For the anxiety and depression patient appears to have an alliance score which are continually rising, while the therapist tends to believe in the other way. We didn't notice such an interaction in the schizophrenia and suicidal patients. You can also visualize the dynamics of their alliance in 3 different scales. Shown here are trajectories colored by different clinical conditions. We quickly notice that the suicidal patient and the therapist tends to diverge in their alliance score throughout the session, and that could have interesting clinical interpretations. We can also use radar plot to visualize how distinct the patient and therapist are in different clinical conditions. So to evaluate our recommendation system, we compare 3 popular reinforcement learning methods. The first one is DDPG, the second one is TD3, and the third one is an offline reinforcement learning method called BCQ. And as we can see from their loss function, they all learn in a very stable fashion over 100 epochs. And to quantitatively evaluate them, we compute the Pearson's correlation between the true actions as well as the predicted action by each recommendation systems in the held out test set. And we see that the BCQ performs the best. And shown here is our demonstration system. We started off with some introduction and instruction about how to play with our system. Then in the quality inventory part, the users get to input their own inventory items. The working alliance inventory is put here as a default. And then on the right, we see there are different rewards, different scoring scales where the users can also change. After that, they finalize it by clicking Analyze Inventory. Then we move on to our dialogue system where the speaker diarization system is being trained. The users usually has to interact with the system for 50 to 100 times to get to relatively stable behavior because it doesn't have any historical data at all. But you can see that the MFCC features are being visualized on the left, and on the right is the weight. Finally, you can see in the quality annotation part, on the left, the current sentences is being transcribed, and you can see it on the left. And also, simultaneously, the alliance score in the grayscale are being computed and visualizes on the right in the bar chart. You can see that when we are seeing different things, it can vary up and down. And that's quite interesting. So our last part consists of our recommendations. You can see it's right below our annotations. We have a suggested next topics for our therapy to take, and our therapist, which by default is the first user, have the option to either take the suggestion and talk about the topics or not take it. So basically that offers additional feedback to the reinforcement learning model. Thank you. If you have any questions, feel free to contact me at baihanlin@columbia.edu.